Okay, it's recording. Those who just joined, I have posted the YouTube video, or the video onto YouTube. It's still processing, but it will be accessible before the end of this session. And then I'll post this session. I'll post after I get home, after dinner or something, and we'll be good to go. So you'll have access to that. And if you don't know where it is, just go to my channel and look at my playlists. It's the 2019 Bootcamp playlist. Okay, so we did all the statistical preliminaries before lunch. This afternoon, we're going to do all of exploratory factor analysis, which is a huge topic, but we're going to condense it down to just an afternoon. Before we do that, though, there is one thing I forgot to do with our data, and that is just clean it out remove all the variables we're not interested in, because there are quite a few variables in this data set that we're not going to use, and that's quite common to collect more data than you're going to use in your model. In fact, I have data sets from all the way back in, let's see, I think 2001 that we've used to publish like 8 or 9 papers just from that one data set. So why collect data more than once if you don't have to? So what we should do is go into our variable view. Also, Magdalene, you're just joining the data sets available in that Google Drive folder I emailed out. And I'm saving all these files to that folder as we go. So if you don't want to follow along but just watch, I'll save the new file in a moment to the Google Drive. So we are using the variables in this model: playfulness, anxiety, experience, usefulness, comp use, information acquisition, decision quality, gender, age, frequency, and social desirability. So any ones that are not part of that, we can just get rid of for now. So adopt is not in there. Is anxiety? Yes. So let me delete these. Oop, escape. There we go, clear. Atypical use, is that in there? Nope. So we'll get rid of atypical use. Comp use, it is in there, so we'll keep that one. So right click and clear. Design expectations fit, not. Efficacy, not. Ease of use, not. Enjoyment is, I believe. Oh no, enjoyment does not. Get rid of enjoyment. And this just makes it easier so you don't have to be dealing with all of the variables. We didn't have to check for missing values on all of them or pattern responses on all of them. Playfulness is in here, so let me keep playfulness. Clear. Repurchase intention, not there. Skill acquisition, not there. Clear. Social desirability is. System satisfaction is not. Information acquisition is. Decision quality is. Unfaithful. This is unfaithful to the intents of the technology. Actually, you know what IRB is, right? You gotta submit your study proposal to the IRB office so that it'll be approved. Here at BYU, we have a reputation for being of high moral standard, and I submitted a proposal to the IRB called The Virtue of Unfaithfulness, because that was the name of my study. But it was unfaithfulness with technology, like using it in a way the designers didn't intend. Yeah, they flagged me on that one and asked me to explain myself. Anyway, let's see. Unfaithfulness, usefulness, we are using. Get rid of this one. And then we'll just leave the rest here for now. Except these two, social desirability, were extras. Let me get rid of those. Okay, and missing was extra. Let me save this as a different file. Save as in that same folder, yep. No missing and trimmed. Should I put 2019 on this? Probably, that would help. There we go, 2019. So that file in that folder is called, is called 2019 Bootcamp Original, no missing, trimmed. That is a really long file name. It should update in Google Drive shortly. And now that we've gone through a morning session, you see sort of the rate at which we go. Who is still following along keystroke for keystroke? Good, okay, okay. then I will continue at the pace I go. Let me know when that file becomes available to you, and we'll move forward. Let's see. Get here. Okay. While that file is becoming available, let me open up my slides for EFA. I'll talk about it a little bit, and then we'll just do it. Okay. Exploratory factor analysis. How did that get so big? That just wants to be in the way. Okay. Oh, sorry. That was loud. Holy cow. That's my error warning sound. Oh. Okay, exploratory factor analysis. In order to understand exploratory factor analysis, you need to understand the difference between a measurement model and a structural model. Measurement model is all this stuff, the stuff on the outside. It's called the outer model. It is the relationship between indicators, items, variables, observed items, whatever you want to call them, measures. They have a bunch of different names. It's those boxes, like CU3 and CU2. Oh, I hear somebody. Okay. It's that relationship there between the latent factor, that is, we have no actual number for those latent factors, like this creativity. All right, somebody, let me mute whoever's. It's Lori. Lori, I'm going to mute you. There we go. Okay. We don't actually have a number for creativity or for learning. Those are not measured anywhere. So we latently measure them with all of these observed, measured variables. Each one of these boxes represents some column in our data set. And combined, we can sort of factor them, group them together to center around some latent idea, some construct. So that's the outer measurement model. The inner model is called the structural model. That's this one, and it's the relationship between variables. It's causal. Whereas out here, technically, this is not a causal relationship. This is a measurement relationship. And the relationship between constructs is a causal relationship, an implied cause, where one thing leads to another thing. So we, in an EFA, are dealing with measurement model. There are actually a bunch of different types of measurement models. EFA is what we'll do today. CFA we'll do tomorrow. And then there's MTMM, which we won't talk about. Hierarchical, which we might get to a little bit. But we're going to focus on EFA and CFA. Who here has never done a CFA? Good to know. Never done an EFA either? Okay. Okay, good. So EFA is exploratory. In fact, this is probably a terrible slide to start with. I should start with this one. An EFA is where you have all these variables in the data set and you plop them down into your software and say, software, find groups for me, groups of variables. You don't tell the software what types of groups you expect, how many groups you expect, although you can tell it how many groups you expect, or what the grouping should look like. You let the software determine that purely based on the covariance matrix, the extent to which each variable is related to every other variable. So that's an EFA, exploratory factor analysis, whereas a CFA, this confirmatory factor analysis, we tell the software, hey, these 5 items go together, these 5 items go together, these 4 go together, and we sort of guide that factor analysis. And people often ask, well, do I have to do both? Why not just do one or the other? What if I already know how my variables are grouped? I know it should look like this thing on the right. So why do I have to do an EFA? And the answer is you need to do an EFA. You need to do it. And here's why. An EFA allows you to explore the discriminant validity issues way better than a CFA. In a CFA, because you're constraining several parameters, you're making it so that you kind of put on blinders and hide some of the issues in the data. Whereas in an EFA, you can see all of those just raw. EFA is very raw. You can see all the discriminant validity issues, the convergent validity issues. They just all come out in an EFA. So always do an EFA. talked about this. You get data from a survey, typically in social sciences, and each set of items together combined becomes some sort of factor or construct. Let's just do it. Ooh, animations. Whoa, trippy. It is distracting. So if each of these is a variable, our job in an EFA is to discover which ones are moving together, which ones are covariate. And as humans, we're actually pretty good at pattern recognition, visual identification of groupings. But you tell me, which ones are actually moving together?
A and E are.
Yeah, A and E seem to be moving pretty slow.
C and F are.
C and F.
D and A are inversely moving.
Are they? D and A seem to be moving together. It's hard with just 5 or 6 variables. You should try it with 50. Right? So that's why we use the software. It identifies it for us. And it shows us exactly which ones are moving together and to what extent. So that's why I could have left that on for 5 more minutes. You just be staring at it. Hypnotic. So what the EFA does is it takes the covariance matrix and it finds how one variable is related to another variable, and then how those 2 variables are related to all of the variables, and then it just keeps churning through all the variables until it finds groupings of variables that are tightly centered around each other, but distant from other groupings. It's sort of like a cluster analysis, but cluster analysis is for rows, whereas factor analysis is for columns. And what it does, it takes that covariance matrix and spits it out as groupings like this into a pattern matrix, which is what we will do. So let's just do it. Is that data now available on Google Drive? Anyone check that?
Yes.
All right. So let's open that one up. Secret SPSS. If you already have SPSS open, don't close it before you open another file. Keep it open so all the drivers are loaded, and then you can close your other file once the other file opens.
Which means you have to leave your old data file open.
And then only close it after the new one opens, yeah. Otherwise, it removes all the drivers from memory, and then it has to reload them all back into memory. Okay. So, those following along, you ready to follow along? Almost? Almost? You're good, you're good. Those who are you all set up and ready? We're good, we're good? Okay. Okay, so what you do in SPSS is you go to Analyze and Dimension Reduction. We're trying to reduce the number of dimensions we have to handle. That's what we do with an EFA. And then go to Factor. Analyze, Dimension Reduction, Factor. And you end up with this. If instead you see all the variable labels, you can right-click inside here and change it to names. Okay. Then what we want to do is we want to throw in all reflective, we haven't talked about reflective really yet, but all reflective latent factor items in here. So for us, that's everything from anxiety down to useful 7. All the ones we're using in our model. Gonna stick them over in here into the variables box. And now we're gonna do a little TurboTax action. We're gonna click on a bunch of buttons and check boxes and radio buttons and pick the ones that we want. So in the descriptives button, let me zoom in. You're gonna check the box for KMO and Bartlett's and reproduced. Why? Because I said so. There are a lot of other boxes. You're welcome to click as many as you want, but make sure you click those as well. These 2 in particular. I also have the initial solution checked. It'll become more apparent why we're checking these once we run the analysis, so you can see what they produce. In the extraction button, there are different methods for doing factor analysis, just like there are different algorithms for running many different types of statistics. A very popular one is PCA, Principal Components Analysis. Another very popular is Maximum Likelihood, ML, and PAF, Principal Axis Factoring. These are probably the most popular among SPSS users. I typically use maximum likelihood because that's also what Amos uses, so it's consistent between the two softwares. However, according to Hare, Joseph Hare in his book, it really doesn't make a big difference. This is a tool. You're just exploring your data. So if one doesn't work, try another one. And we may end up doing that. We'll see. Extraction, this little frame here, we're going to extract based on eigenvalues. Eigenvalue is it's an indication of the value or contribution of a factor. We'll talk about that when we look at the output. But if we wanted to fix it to like only a certain number of factors to be extracted, because we expect, zoom out, we expect, oh, I put the model away. We expect 2, 4, 6 factors, I think. So we could say we want 6. Although we added a couple more for social desirability. Okay, continue. Rotation. Just as with the factoring method, there are different rotation methods. Rotation, the non-complicated explanation of rotation is it separates factors more. So the distance between groupings is larger. That's rotation. There's more to it, but that'll do. The two most popular are Varimax and Promax. Varimax is sort of a soft solution. It's good when you have extreme values, like really low loadings, really high loadings. But I use Promax. It's fast, it's clean, it's robust. And continue. Excuse me. Don't worry about anything in scores right now, although we might use that later. In the options, I do want to suppress small coefficients. I'm going to say absolute value is less than 0.3. This is going to produce a pattern matrix. It's this massive matrix of numbers, of loadings on factors. And it's really messy and hard to read. But we can suppress, meaning hide, any loadings that are just too small to care about. And so that's what we're doing here. We're suppressing the ones that are just too small to care about. Continue. And it probably feels like you just followed along, press buttons, you didn't know what you're doing. That's fine. It'll make more sense as we do it. So hit OK. And let's talk through all of this output. I wish that was bigger. Here we go. That's more readable. All right. So the KMO, it's to what extent are all the variables we just included in this model actually related to each other? Are they sufficiently correlated to justify doing an EFA? Because one of the main assumptions of the EFA is correlated variables. If your variables aren't correlated, they don't belong in an EFA. Anything above a 0.8 is considered pretty good. Above 0.9 is fabulous, so we're good. Anything less than a 0.6 is very questionable. So if you have less than a 0.6 here, it's probably because your variables belong to formative factors instead of reflective. Again, we haven't really talked about that, but it's because the indicators for your factors aren't required to be correlated. The questions we asked in our survey, I'll show you, were highly, highly redundant. For example, for decision, here's anxiety. For anxiety, 1, 2, 3, and 4. I'm unable to keep up with important advances in technology. New computer technology makes me feel uncomfortable. I get a sinking feeling when I think of trying to use new computer technology. New computer technologies scare me. These are all highly correlated conceptually. And that's the assumption of an EFA, is you have highly correlated indicators for each factor. If you're getting a low KMO, it's because you don't have highly correlated indicators. You have more formative indicators, which means each item represents a separate dimension of that factor, which may or may not be correlated. You might also get a low KMO if you include demographic or categorical type variables, nominal variables in here. Those don't really belong. So for example, I didn't include gender or marital status or child order in my EFA. Okay, communalities. This is another look at the adequacy of the correlations between the variables. In the extracted column, we want extraction values greater than 0.2, 0.3. It looks like we're pretty good. Social desirability is a little low, especially number 10 there. That's pretty low. We might have an issue there. Do we make any decisions based on this? Not really. It's just sort of flagging. We'll want to check out social desirability 10 when we get down below.
Those are commonalities, right? You kind of
Yeah, they're essentially commonalities.
You want to take a quick gloss though, see if they're over 0.5, right?
Are you concerned if they're over 0.5? Or are you happy? Yeah, 0.3 would be our general cutoff for commonalities. Okay, this table, it's all good. This table, the total variance explained table, we see a few things. On the left, we see eigenvalues. Well, on the very far left, we see the factor number. Whenever you're doing a factor analysis, it actually runs everything from 1 to the number of items you have. So we included in our factor analysis, we included all those items. There were 47 items we included. So it runs from 1 to 47 factors, solutions, to see if that works. And if you run it where every item is its own factor, you can explain 100% of the variance in the model because everything is itself. It's like correlating something with itself, right? The correlation is 1. Same idea here. If every factor is accounting for itself, then you have 100% variance explained. So we don't want that. We want to reduce dimensions down to just highly contributing factors or groupings. And the way we look at the contribution of a factor is by its eigenvalue. Again, that's a measure of contribution. And what is it contributing? It's contributing a % of explained variance. Higher is better. Greater than 1 is considered the cutoff, although we can have a little bit of wiggle room there. If we look at the % of cumulative variance explained, we're looking at actually over in the extracted column here, extracted cumulative variance explained. We're looking for above 50%. You want more than half of the variance to be explained by the model, not by error. Above 60% is better. That means you have a pretty good model. In our case, we're 57. That's tolerable. It's pretty good. Let's go down. Zoom out. There we go. Ignore the factor matrix. Just ignore it. It's mostly useless. Goodness of fit test can also ignore this if you want. The general rule of thumb is you want the chi-squared divided by the degrees of freedom to be somewhere between 1 and 3. In our case, we're right there. We're at like 2, a little less than 2. So it means we have a pretty good model. But it's a terrible measure, so nobody uses it. This one, the redundancies table, ignore the whole table, but just look at the bottom. And this says how much, to what extent, essentially, is their variance explained by error. And in this case, it's about 5%. Extra. You want it less than 5%, although some people say less than 50%. So we don't really use that, but it's a good internal measure. You probably wouldn't report this number, but you can look at it and be like, oh, my model's terrible, or oh, my model's not so bad. So in this case, our model's not so bad. It's 5%. This is your bread and your butter right here, the pattern matrix. This is what you want to focus your time on. This shows you how every item loads into groups. Remember, we're suppressing small loadings, less than 0.3. Which means we're not going to see those. Every item, though, is loading on every factor. So like anxiety 1 is loading on all 9 factors. It's just loading less than 0.3 on every factor except factor 3. Do you have a question?
Yeah, I have a quick question. I'm wondering, how does it choose to load on a certain factor? Like why?
Yeah.
If I run 2 different pattern matrices, which I've done with a hypothetical capstone database, I get a pretty pattern matrix, my commonalities and all that stuff is the same, but they've loaded on different factors. And the only thing I've done differently was one's PAF, one's ML. Mm-hmm.
So how does it decide which factor to load on?
Be a concern in terms of like 1 through 7 in that regard?
So the ordering, you're asking about the ordering, like why is anxiety all loading on factor 3, right? Why not factor 1?
Right, so like factor 1, on one of them was set 1 through set 5.
Yeah.
And my other one, prod 1 through prod 4.
Yeah. So why is this grouping on factor 1 and not on factor 2? SPSS, when you're doing ML, the default is to put the strongest loadings on factor 1. So in this case, the strongest loadings, I bet, are usefulness. Let's zoom out and see. Yep, it's usefulness. Notice the loadings on this one are really high, 0.8, 0.9, a couple 0.7s. So these are the highest loadings. It's going to shift all of that over to factor 1. It's the first factor that emerged and explained the most variance. So usefulness explains the most variance, which means usefulness is the most highly correlated factor with all other items in the model. The least correlated factor would be everything on factor 9, which is, what's on factor 9? Nothing? Nothing. All right, so factor 9 is useless. There are things there, they're just not loading above 0.3. So that's something to think about. We'll look at that in just a sec. There's somebody on chat. Zoom in really helps me see better. Okay, I will keep zooming in. Thanks for the feedback. Okay, so in terms of contribution, factor 1 is the greatest contributing factor. Factor 2 is the next greatest, and so on. The least contributing is this factor 9, where nothing really loads very strongly, and then factor 8, where it's just these two little items, and so on. So let's mess with this a little bit. What we want to see is we want to see every factor have items. So factor 9 is a problem right now. And we want to see every item loading on at least, well, hopefully just one factor very strongly. So if we look at these anxiety items on factor 3, we want all these loadings above about 0.5 and ideally averaging out above 0.7. Here's why. There's a measure of convergence on a factor. It's called convergent validity. And the measure itself is called average variance extracted. And you want that average variance above 50%. And when you square 0.7, that gives you about 50%. And so we want the averages here about 0.7 or above. In this case, we're doing great. We're averaging out about 0.8 something. So anxiety is fabulous. You don't want items loading less than about 0.5 because those, in terms of groupings, and people remotely can't see my hand. In terms of groupings, let's say you threw a bunch of M&Ms on a table and there were like 5 all stuck together real close by, and there was one dangling out 5 inches away. That one dangling out 5 inches away isn't really part of that group, but that's what that low loading is saying, is it's still part of the group, but it's very loosely connected to the group. And so you don't want really low loadings, and the threshold there is about 0.5. So if with some caveats, you don't want to reduce a factor down to less than 4 items if you can help it. So like this one, comp use, if we had a 0.4 loading here, I might not delete it just because I don't want to remove too many items from comp use.
James,
yeah.
When you suppress below 0.3,
yeah,
were you then eliminating discriminant validity there, because there's no cross loadings coming up here? Is that
right? So when I suppressed below 0.3, I was really just filtering for visual benefit, so I wouldn't be seeing. Let me show you what happens when we don't suppress. Don't follow me, just watch. I'm going to go over here, and I'm not going to suppress at all. Continue. Okay. And I go down to the pattern matrix right here. Here's the new pattern matrix. It's actually the exact same pattern matrix. It's just now we're seeing all the loadings. If I zoom in, you can see anxiety still loads on factor 3, but it also loads everywhere else. But it's just all less than 0.3. And so we don't view it.
The default's 1. Sometimes I just use the default.
Right. So I don't use the default because I don't want anything less than 0.5 on there anyway. And so, I mean, if it's...
Is that how we consider discriminant validity when they cross-load like that?
Yeah, let's talk about discriminant validity. Let's go look at our previous factor analysis here, our pattern matrix. So I was talking about convergent validity essentially with the last thing, where you want high loadings, average up, converging, you want tightness within that factor, nice high loadings. Discriminant validity would be you don't want variables from one factor to load onto a different factor. So for example, if anxiety 6 loaded on factor 5, that'd be a problem because it doesn't belong there. Theoretically, we already have a model in our head of which items belong to which factors. We don't want them jumping to other factors. That would mean they're more related to that factor than to their home factor. That's a discriminant validity issue. In terms of visualizing that, it's if you had 2 clusters of items, it's if one of the items from one cluster was overlapping the other cluster of items. And so you don't want that, because then you don't know which factor it really belongs to.
Can I ask you a question?
Of course.
So whenever you had no, well, you took away those constraints, right? You had some that showed up negative, but that doesn't, I was under the impression whenever you had things loading on a pattern matrix and they were negative, that was a reverse coding issue. That is not.
So yeah, notice we have some negative loadings.
Yeah.
In this case, it just means it's inversely correlated.
Okay.
Yeah. So as the value of that item increases, the general trend of the that factor decreases.
But should we be aiming for no negative?
You should not be aiming for no negative loadings unless they're the non-suppressed ones. The primary loadings should be positive.
Okay. That, yes, I didn't phrase that well, but that was my question.
So you have primary and secondary loadings. So in this case, let's zoom back in. Primary loadings on factor 3 are anxiety 1 through 7.
Right.
Those are the primary loadings. These other loadings over here, like 0.002, the negative 0.002, that's a secondary loading.
And that's okay if it's negative.
Totally fine if it's negative. Yep. As long as it's not negative and strong. You still want the absolute value of the difference to be kind of far away, like more than 0.2 away. Yeah. So like here's 0.651, my primary loading. I wouldn't want a secondary loading of 0.6 somewhere else or 0.7 somewhere else. Definitely not higher. That'd be terrible. Or even negative 0.5 or 6. That would worry me because it would feel like it was the same factor. Okay. Back here, let's look at some of these. So anxiety looks great in terms of discriminant validity and convergent validity. It's loading on its own factor. It's not loading anywhere else. That's great. Comp use looks pretty good. It's not as strong. It's not loading anywhere else, so we're good. Let's scroll down. Playful looks really good, really, really good. There's this loading that's kind of low, but it's not terribly low, so we'll keep it. It's not loading anywhere else. Social desirability. Poop. That is unfortunate. Notice, first off, we have positive loadings and negative loadings on social desirability. Why? Because we have positively skewed bias questions and negatively, not skewed, positive bias questions and negative bias questions. If we go back to the wording here on social desirability, it's these ones right here. Zoom in. You can see the top few. I'm always willing to admit when I make a mistake. Very positive. I try to practice what I preach. Also positive. Let's go down a little. I like to gossip. I sometimes try to get even rather than forgive and forget. At times I really insist on having things my way. Very negatively worded. So these are all getting at the same thing, but in opposite, with opposite approaches. So they all load on the same factor, but the bottom 4 are inverse to the top 5. So what do we do with that? To be honest, we're not terribly concerned. It's a eventually what's called a specific bias variable. It's a control variable. We're not theorizing about it. It's not going to be predicting anything. It's just something we're accounting for. So if the validity is not fabulous, we're not too concerned. Yeah.
Wouldn't that be true also if you use it as reverse scaled items?
For reverse scale, see now the thing with the reverse scaled items, I hate reverse scaled items. They never load properly because people don't treat them the same way as positively coded items. So we could have, with anxiety, for example, we could have said, these are all like, get a sinking feeling in my gut when I use computers. We could have said, I'm super confident when I use computers, negatively worded compared to the trend of the construct. And it wouldn't have loaded on there very well, or it would have been an inverse loading and probably would have been a low inverse loading, like a negative 0.4 or something like that. And so what we do if we have reverse coded, we would actually go back into the data set, re-reverse the value by subtracting it from 1 more than the scale size. So like if you say 1 to 5 scale, you subtract from 6 to get it to a positive code. And then you stick it back in here so it loads positively. Reverse coded items, I almost never use them just because they almost never load properly. No.
But in this case, would an appropriate intervention be to reverse code the negatively coded ones?
So we could, yeah, if we wanted to keep social desirability altogether, we could re-reverse those and it would just put them all in the same factor. Or we could treat it as 2 separate dimensions. That's one way to do it. Yeah, and that's what I prefer to do, I think.
So how come SPSS didn't try to make those 2 different factors?
They were too highly correlated. Let's see, question from Zoom. What do we do if 2 different constructs from literature are loading together very strongly? Let's cover that in one moment. Make sure I get to that. I'll show you in a sec. In fact, we'll try to do this with social desirability. Give me just a sec. Okay. So let's come back to social desirability because it's of our least concern. Come back in, information acquisition. Looks pretty good. Oh, look at this loading. 0.496. That's really close. It's like really, really close to 0.5. I'm just going to keep it. This is exploratory anyway. If this were a confirmatory factor analysis, I may say, lop it off. But this is exploratory. It's close enough. It's just a tool. Decision quality. Oh, we have some issues. Huh. They double load on this imaginary 8th factor, and there's some issues there. I wonder what, looks like the top loads really well. What's this? Let's see, decision quality 11, 12, and 13. Always go back to the wording. Here we go, decision quality. Was it 9? No, 10, 11.
11, 12, and 13.
11, 12, and 13, thank you. 11, 12, and 13. Compared to the ones above them. Let's see, Windows. So the ones above them, Excel helps me make higher quality decisions, helps me in my decision making process, helps me make decisions that are more correct. So those are all about higher quality. Now these 3 that didn't load very well, helps me make decisions more quickly. Oh, that's speed and efficiency. Helps me make decisions in which I can be confident. Also slightly different. Helps me involve others in making decisions. That's a totally different thing. You can see why these didn't load together. Conceptually, they're not highly correlated. So I might even say these are not what I was looking for. What I'm looking for is high quality decisions, which is up here. So I would just delete those 3 because they're not relevant to what I'm looking for. Before I do that though, let's look at usefulness, and it's looking fabulous. So we have a couple decisions we need to make at this point. And a couple things we can do. We have 2 extra factors we weren't expecting, and they're both garbage. So we could constrain, we could constrain it down to 7 factors and see what happens. And we also have 3 variables here that we didn't intend to include, 11, 12, and 13 of decision quality. Let's do this first. Let's delete those 3 variables because they are what's causing this 8th factor. So let's delete those 3 and see what happens.
Why are you going to delete 12?
12, wasn't it about confidence in decisions? Or you can be confident about your decisions even if they're not good decisions.
Well, you're saying based on the stats, though, it's like, I mean, you're not hard up for items in this.
Not at all, which is why I'm willing to just throw it out. We could start with number 11 and get rid of that one.
See, 11 is a better loading than 6.
6. Oh yeah, 5 to 8 there. Yeah. You mean 12 is? Yeah, 12 is. Let's look at number 6 real quick.
The 12 cross loads.
Ah, see, this is another one. Excel helps me identify problems. This is number 6, which was loading low. So is that what I was looking for? Well, not really. I'm looking at effective, high-quality decisions, which would be these ones right here, these 4. The rest are meh, not exactly what I was looking for. Although, you're right, we might count also this one, number 12. So, ignoring statistics for a moment and basing it purely on conceptual relationships, let's do this. Let's get rid of number 6 and number 11 and 13. So back to factor analysis. Down to decision quality. Get rid of 6 and 11 and 13 because these weren't really what we were looking for. And I need to reset my options here to suppress and 0.3. Okay. All right, and we run this. Notice every time we add or remove variables, the KMO will change. Our KMO dropped slightly. It's not that bad. Our communalities will also change. Not that bad. Social desirability has small issues still. Number 10 especially, that's pretty low. Our total variance explained will have changed, and the number of factors extracted will have changed. Except in this case, where it's still extracted 9. Okay, let's jump down to the pattern matrix and see. Here we go, and we're gonna look at decision quality first, because that's the one we changed. And it looks a lot better. That looks pretty good. I say we keep it. Are there any cross loadings? Nope, no cross loadings. That looks pretty good. Okay, the next issue then is, are there any other cross loadings? Anxiety 2 has an issue, and usefulness 3. Well, let's try this. Let's just force it to 7 factors and see what that looks like. So back in factor analysis, in the extraction, you can say instead of extracting based on eigenvalues, extract exactly 7. I want 7 factors. No more, no less. Hit continue, hit OK. And just jump straight down to the pattern matrix. And anxiety 3 fixed itself. Looks good, looks good. Still some issue here, but information acquisition looks mostly good. Decision quality looks good, and usefulness, that one that was double loading, looks good. Okay, so we're good in terms of convergence and discriminants, except when it comes to social desirability, first half, second half, although we expected those to load together. So let's do this. What I would do is I would keep track of what we've removed, which we can do here. Let me go look at the factor analysis. We can see on the left what we've removed. Decision quality 6, 11, 13, and that's it. So just got to remember those 3. And what we're going to do is we're going to do a factor analysis. Here's a question from the remote folks. What does the 7 mean? Oh, 7 is the exact number of factors I want extracted. So whereas before it was extracting however many factors had eigenvalues greater than 1, they were contributing, substantial variance explained. This time I said, forget eigenvalues, just do exactly 7 factors. All right. What do we do in case we have the same variable with different items that are reversed? The same variable with different, like you're measuring, let's say it's job satisfaction, and 3 of the variables are positive and then 1 is reversed. Is that what you mean, Naveen?
Yes. Yes.
Okay. In that case, what you would do is you'd re-reverse the reverse coded items. The way you do that is in SPSS, let's go to the data here. What you would do, let me close that. Let's say, for example, playfulness 7 here was reversed. It's on a 5-point scale, so I would subtract all of its values that are there from 6, because that's 1 more than the 5-point scale. And so a 1 would become a 5, a 2 would become a 4, a 3 would stay a 3, a 4 would become a 2, and a 5 would become a 1. And the way you can do that in SPSS is you go to transform, compute variable, and we'd call this new variable, playful 7 unreversed or something like that. I'll just give it an R here.
You don't do it in record?
Sorry, what?
Recode?
Recode? No, you wouldn't have to recode. You just do it right here. And so I just do playful 7, 6 minus playful 7, and that would create a new variable in my data set. If I go back to my data set, go look to the right, here's playful 7R, and it's just 6 minus whatever value was there. And then I'd use that one instead of the original one. Cool. All right. So I was going to show you, sorry?
What happens if I do recode and then I just reverse the scale? And
then if you recode and you just re-reversed it, then it should load with its appropriate factor.
Okay, great.
Positively, yeah.
Thank you.
You're welcome. So we had an issue with social desirability, 1 through 10. If we stick this in here in its own factor analysis by itself, and this could be for this, it could be for any 2 factors that are sticking together. And then we force the extraction to 2 variables. This will force it apart, and we can see where the cross-loadings happen. So I'm going to hit OK, and in the options, I'm not going to suppress small coefficients. I want to see all loadings, so I can see where the cross-loadings are. Hit Continue, and OK, and this forces it out to 2 factors. And you see factor 1, let me zoom in. Factor 1 is all these positive ones, 1 through 5, and then factor 2, yeah, that didn't work very well. They're too highly correlated. Usually this will separate them. Yeah. Problem is it's the same factor. It's not 2 separate factors. So this won't work very well. Dang. A better example would be with a different data set. I'll show you now. Give me just a sec. Let me show you this. Don't follow along, just watch for a sec. Because this is a common issue. Let me pull up this new one here, this original. This is a common issue where you have 2 factors that load onto the same factor. So just watch, don't follow along. I'm going to throw together a factor analysis where I'm pretty sure stuff will just load together. System satisfaction and usefulness. I bet there's one more up here we can throw in here. Playful, enjoyment, ease of use, efficacy. I bet that'll be in there. I bet one of these is going to load together. Just in case, I'll throw in a decision quality and information acquisition. There you go. Something here is going to load together. Got that. Just setting this up, and let me suppress. Okay, please break. And, oh, system satisfaction broke in 2, but nothing loaded onto itself. Dang, onto another factor. Well, what you would do is if you had that situation, my data's too good. What you would do is you would throw those the items from those 2 factors into a single factor analysis, force it to 2, and then look at where the cross-loadings were. You look see which ones were the highest cross-loading, and then you delete one item at a time, starting with the highest cross-loading. And that would separate and separate. In fact, I can show you, check this out. This will be a good illustration here. Let's go like this. Actually, let me get rid of those as well. And I'll get rid of well, start there. Okay. Check this out. If I do extract, there we go, and then in here, loadings plot. In the rotation, if you do a loadings plot with 2 factors, then what you can see down here in the loadings plot, here is the actual groupings of items visually depicted. And when you do a factor analysis with just 2 factors, it should show you those groupings, and then you can see which ones are closest. So in this case, decision quality 6 is the one that's closest to the information acquisition factor. If I eliminated decision quality 6, it would space out these factors even more, and they'd be more distinct from each other. And so that's how you could distinguish the two factors from each other, is by looking at this loadings plot. So if I get rid of decision quality 6, for example, let's go do that. Get rid of that, run it again, go down to that plot, and you can see they are now more distinct, more separate than before. You also see up in the pattern matrix, they load very cleanly separately from each other. So that's how you do it if you had two loading together. Just separate one item at a time looking at that loadings plot. Yeah. Okay. Back to the pattern matrix not that one. Oh, I'm in a different data set. Ah. This one. This is where we ended. Okay. We have a pretty good pattern matrix, which means we have a pretty good EFA. If this wasn't working, I should have dirtier data. It would help. We could see more edge cases. What you could do is go into your factor analysis. Let me reset this to, oh, wrong data. All right, let me close that other data set so we don't get confused. There we go. You can go into your factor analysis, add back in all the stuff that we took out. Except we got rid of decision quality 13, 11, and 6, I believe. There we go. Go like, fix it to 7, right? 7. Okay, so if it wasn't working, what you could do is you could try different extraction methods. So I use maximum likelihood here. Try it, everyone. Try principal components. See if it helps. See if it changes. I'm gonna hit OK. Let's see. Go to the pattern matrix down here. Oh, I'm not suppressing. Let me go suppress, so it's more visible, more readable. Okay, and jump down. All right, and you see with oh, hey, whoa! Look at this! Hallelujah! Check it out. Social desirability 1 through 4 and 6 through 10, they separated. That was totally on purpose. I just played dumb. Yeah. All right, wow, sweet.
Which extraction method?
I used principal components on that one, and it worked really good. Haha. Typically, principal components generates higher loadings, so if you're having trouble with convergence, you might try principal components. This separated it. Now, check this out. This one loaded in both places, and this one loaded inversely on the wrong factor. So what should we do? Well, what I'd like to do, zoom out, is see if I have, oh, not there. I want to maybe try removing social desirability 5 and see if that separates both of them. So I'm just gonna run this again. Remove social desirability 5, hit OK, jump down to the pattern matrix, and look at that. Beautiful, beautiful. Uh-oh. Check it out. Information acquisition and decision quality. Oh, but remember, we forced this to 7 factors. So it had to collapse something. So let's go back, factor analysis, extraction, just do it based on eigenvalues. See what happens. Jump down to the pattern matrix. And there we go. Hey, look at that. That's pretty good. That's clean. We could report that. That's nice. Okay. So once you got that, and if that didn't work, we could try principal axis factoring. I just want to show you what the difference is. So I'm going to run this as principal axis factoring. And these do actually have different algorithms, and something different is going on under the hood with each one. But again, it's a tool to explore your data. You can see the loadings are a little bit lower in principal axis factoring, but it's separated pretty nicely. So maximum likelihood was what was causing our collapsing here. Nice. Once you have a factor analysis that you're pretty pleased with, you want to check a couple more things. You want to go down to the correlation matrix down at the bottom, And make sure there aren't any correlations greater than 7, or 0.7, I guess. Because again, if you square a correlation greater than 0.7, then you have over 50% shared variance, which is not good. So we look at all these non-diagonal values. We're looking pretty good. The highest one I saw was 636, which is between 4 and 5, which is probably information acquisition decision quality. Let's check. Factors 4 and 5. Here it is. 4 and 5 are, yep, information acquisition decision quality. They're highly related, but they're not so highly related that their correlation's above 0.7. So we're good. That means there's discriminant validity between them. So we're good there. We talked about the AVE, right? The averaging pattern matrix loadings above 0.7. We're good there, except with social desirability, which we don't care about that much. The last thing to do with an EFA, wow, that went by, is to look at reliabilities. So we want to make sure each factor with its remaining items is actually a reliable factor, is consistent, that its loadings are consistent and its error is consistent as well. So what we do is in Analyze, we go down to Scale, Reliability Analysis. Click on that, and then we check each factor. Excuse me. So social desirability 1 through 4, we go look at that, stick those items in there, and hit OK. And we're looking for Cronbach's alphas greater than 0.7, ideally, but down to 0.6 is okay for a specific bias variable like social desirability. And the more items we have, the stronger our Cronbach's alpha should be, meaning the more reliable it should be. The fewer items, like 3 or 4 items, we're probably good down to 0.6. So we want to check that for each one. I'll do it for a few. That's that one. Let's do it for anxiety. We kept all of those, right? 1 through 7. Stick that in there. Hit OK. And you can see we have a 0.934. That's fabulous. Great Cronbach's alpha. You would report this. Typically what I like to do is I like to take my pattern matrix, my final pattern matrix, this one, just copy it out to Word. And paste it in there. And then at the top of my pattern matrix, instead of having the factor numbers, because those are intuitive, I just stick my Cronbach's alpha. So for factor 7 that we checked, it was what, 0.634 or something like that, 0.634. And for anxiety, it was, that's factor 2, 0.9 something, 0.9 something. Down here, let's see, reliability was 619 and 934. Something like that. And then just call this Cronbach's alpha, CA. Something like that. And then you can fit all on one table. And that way you don't have to take up a lot of space with your EFA, which nobody wants to see anyway in a report. You might stick it in your appendix. Yeah.
Hypothetically, down the road, you do your CFA, you're doing some invariance or method bias testing, you find some items that are causing problems, you remove them, you need to circle all the way back and do like this reliability check?
Oh, that's a really good question. I get this question all the time. For the remote folks who couldn't hear it, let's say you finish your EFA, it looks great, you do your CFA and you get halfway through your CFA, and turns out you got to remove an item due to method bias or model fit or whatever it is. Do you then have to go back and redo your EFA to match your CFA? The answer is no. Your EFA is a tool to understand the relationships, your measurement relationships, and then you just use that as input into your CFA, but you never have to go backwards into your EFA. Good question.
But then the alpha will be changed if I remove.
Correct, yeah. So your Cronbach's alpha, which was reported from your EFA, will not match your composite reliability from your CFA.
So I have to go back and recalculate it.
if you want the Cronbach's alpha for the final set of items, sure. What I use is, in EFA, I use the Cronbach's alpha, but then in the CFA, I use composite reliability, CR. And so that would be the more current final set of reliability measure.
Can you explain how we can divide the Cronbach alpha for males and females?
Oh yeah, sure. If you want to do this separately for male and female, definitely. So what you do, if you want to do a separate CR or Cronbach's alpha for male and female, what you do is you go to Data, Split File. Data split file. This won't cause permanent changes, so you can just click it without any hesitation. And then that brings up this, and what you'll do is you're going to compare or organize output by groups. So let's do a compare, that'll put them in the same table. And we want to compare groups based on, for this one, gender. So stick gender over in the groups based on. And then hit OK. And now any test we run will be separated by gender. Every single analysis. So if we run a regression, it's separated by gender. If we run a ANOVA, separated by gender. If we run an EFA, it'll be separated by gender. Here's a reliability analysis. Run this again. And notice the output is organized here and compared across gender. Here's Cronbach's alpha for male and for female. And then if you want to undo what you just did, just go back to data split file and hit reset. And that'll undo the splitting, and now all your analyses will not be split by gender. That's pretty handy. Whoops.
Thank you.
You're welcome. Lori, going back, why subtract from 6? Yeah, sorry I didn't explain that very well. A while ago, I subtracted all the playful 7 items from 6, and it was because we were pretending that that was a reverse-coded question, where a high number on that scale would imply a low amount of playfulness. And so since the scale is out of 5, it's like strongly disagree to strongly agree, 5 points. If we subtract all those values from 6, then we end up turning all the 1s into 5s, all the 5s into 1s, and all the 2s into 4s, and 4s into 2s, and 3 stays the same. So it just creates numbers that are consistent with the intention of the trait we're trying to capture. So a higher value on the scale now, after subtracting, would actually mean more playfulness. So it's positively coded. That's the way we did that. Okay, I don't know how I moved this down here. There we go. Okay. Any other questions on EFA? That was EFA. Oh, it's a lot of stuff. You can also split your EFA, overcoming a negative question. Please clarify. You can say it out loud too if you just want to jump on the mic. While you're doing that, you can split an EFA also without going to split file. You can just go to factor analysis, and you can just run it for one gender. So I could say down here, I could put gender in the selection variable. Yeah, so that's where I can say, I just want to run this for males, 1, hit continue, and it's going to do my EFA just for males. And I can go back and try it again just for females. Whoever's on the mic, I can hear you. I'm just talking over you, which is why it's muting your sound. Sorry. Let me stop talking in just a sec. Here it is for females, same EFA, just for females. Okay, let me reset that and then stop talking. All right, whoever's remote and you wanted to talk, let's get to it.
A question about subtracting from 6. So if the question
I can't hear you. If you could talk like a lot louder, that'd be great.
My question is about subtracting from 6. If the playfulness question was phrased negatively, then subtracting from 6 reverses the values, and that's why you did it?
Yes, that is correct.
Okay, cool. Thank you.
You're welcome. She was asking if if the reason we subtracted from 6 is to overcome the negative wording of a question. Yes, that's why we did that. Okay. Wow, let me go back to the slides and make sure I didn't miss anything, because we just burned through that in an hour.
Slightly off topic.
Yeah.
What's going to happen when gender gets erased, or it's not possible for us to discuss the topic?
So actually, I was designing a study the other day, and the co-authors and me, we were trying to figure out how we were going to account for gender. Right. Because more and more people don't want to report I'm male or I'm female. They want to report some sort of spectrum.
Even are not.
Yeah. And so the way to overcome that scientifically, like collecting data-wise, would be to provide a masculinity scale or a femininity scale or something like that, or just more options. But I tried to, in one of my studies, I tried to do a masculinity scale where far right would be I'm a tough dude, right? And far left would be I'm a feminine, not dude, whatever. And males and females can answer the same scale, sure. And we just get a scale of gender identity. And the reviewers didn't go for it.
No,
yeah.
I wouldn't think so.
But I thought it was clever.
I think it's clever. I can't see very many people liking it.
Yeah, it'd be like you take the survey and you start realizing things about yourself.
Like,
yeah. So, yeah. I don't know if there's a good way yet. What people have been doing is just providing more options, saying I identify, not gender. It's right. I identify as male, female, non-binary, and that's usually where it's cut or other, and then cut, and then you can have multiple others.
What if it was color coded by Roy G. Biv?
I don't know what we do with that. Color coded.
Right.
Like I'm a.
Like on
green.
A scale of,
I'm brown. I'm totally brown.
Pink to blue.
Oh, pink to blue. Okay. Yeah, you could do that too. Same idea as masculinity scale. Yeah.
I think you need to be careful with that.
Because some people say
cultural awareness.
Yeah.
Well, but,
pink isn't female.
But you could choose the color of your choice. I mean, what's green?
Right. So anyway, yeah, you have to come up with creative ways around it. The key though is you want to make sure you're measuring what you think you're measuring. Yeah, because otherwise your science is useless. Your results are useless because
it's gonna really kill them.
Yeah, especially gender in particular. If you say men are like this and women are like this, well, what if the men who reported their gender as male don't actually identify as male, and then you've messed things up. Yeah, so it is a valid point. Okay, here we go. Applications, we talked about this. It's a tool. It's for reducing dimensions, confirming what you thought you were measuring. Why do we do it? Well, because this is what we theorize, right? We theorize a bunch of factors predicting each other. But what we're measuring is actually here a bunch of variables that represent each of these factors. And the way they're related to each other, represented here by their distance from each other, isn't as clean as boxes and arrows. What it is really, you got this blob that represents that one factor and this blob that represents that other factor and so on. And there's a lot of overlapping covariance, shared variance between these factors. And so what you end up testing is this, unless you do a factor analysis to reduce these factors into more tightly correlated sets of items that are distinct from each other. So what you end up doing in an EFA, pop them all back up there, is you say, well, this green one isn't really tightly correlated with all the green ones, and this red one doesn't seem to belong to the red ones, so let's lop it off. And then, oh, these are really tightly correlated, but they're not part of anything we actually measured. And red, what's going on with red? None of them are tightly related to any of each other. And so you end up lopping off a bunch and then maybe finding a new factor. And that's why you do exploratory factor analysis, is to identify how things are actually correlated. And so once you do that and you reduce it to these 4 items and these 5 items, then you're actually testing what you're theorizing. Whereas if you were to just throw all the items into a CFA and call it good, and then, or just average them, that's the worst. If you were just to average your items and then run regressions, you would have been testing that. And who knows what that means? It's not valid science. So that's why we do the EFA.
Okay, so
Yeah.
you do your EFA and then you get your factors that are nice and clean.
Yeah.
At the end of the day, you're still just kind of averaging or summing the elements, are you not?
No, we haven't gotten there yet. That's a step I missed. Okay, so what you can do with a factor analysis is, now that we have our sets of items that we know are strongly correlated, we could average them or sum them, have a summative score. But why do that when you have the power of a factor analysis? You have now weighted loadings that are relatively scaled to each other, that represent the distance from some sort of centroid of correlations among the items. So why not use those to have a weighted score for each factor? So you can do that too.
You weight it by the loadings.
Yeah, you weight it by the
If
loadings.
happens to be negative, you weight it by a negative loading.
If the weighting happens to be negative, you're going to mess things up. But yeah, it would come in with a negative impact. Yeah, but in an EFA, you can do this automatically. If in your EFA factor analysis, this button that we never clicked on, that I told you not to click on, you're now old enough to click on this button. Yeah, you've arrived at a stage in life where I can explain this button to you. This is a little awkward.
You can take 2 aspirins now.
That's right. So hidden in this button, there's this option to save factor scores as variables. And this will compute a weighted score, a weighted average that I don't remember if they standardize it. I don't think they standardize it, but I'll check. But it computes a weighted average for each of these factors, taking into account the weights of the loadings on those in the pattern matrix. So if I do this, check this out, hit continue, just use the regression approach. These other ones are valid, but regression is the one we'll use. Continue and hit OK. Then what happens, zoom out, is in my data set, after I run this, let's go back to the data set, you'll see I have 8 new variables, each representing the factors. Now we have to be very careful. It looks like it did standardize it, which means it set the mean to 0 and the standard deviation to 1. So they're all roughly normal and same scaled, like with each other. What you have to be careful of, though, is what each of these represent. So factor 1 represents, we have to go to our pattern matrix. It represents usefulness, the ones that loaded on factor 1. So what we'd want to do is go back to our data set, go to variable view, go to the bottom here, and rename this usefulness. And maybe put an F on there so we know it's our factor score, FS or something like that. And then we have to go find what was on factor 2, anxiety. We call this anxiety, FS, something like that. And so now we have factor scores for all of them. We can run regressions if we want, or we can actually just skip this step, go to our CFA, our confirmatory factor analysis, further refine the model, and then extract factor scores. Or never extract factor scores. You can do that too. Just run latent analyses.
The input into the CFA, though, is the item measurements,
not the factor scores.
Factor scores, but is there some way that we can get the loadings into the CFA without manually having to do that?
Yes, there is. There's a way to automatically generate a CFA model based purely on the pattern matrix. No manual manipulation involved. You're welcome. I created a plugin for it. I'll show you when we get to CFA. Yeah. But yeah, it's a pain in the rear to create a CFA from scratch, which we'll have to do because some of you won't have the plugin, or the plugin won't work for you, or if you're using Mac and you're on SPSS on your Mac side and Amos on your Windows side, it doesn't work. So we'll create it manually as well. All right, back to the slides. Okay, so yeah, dimension reduction. Question from remote folks. How do we justify if we found a new construct given it doesn't come from theory? Ooh, good question. Yeah, so back over here, oh, minimize. Back over here, this new factor, this thing, what is this thing? Well, we'd have to look at the wording of the questions. And this actually happened to me with this data set. So with this data set, before the boot camp, And when I initially designed it, these questions right here, information acquisition and decision quality, I had as a single construct. I called it system usefulness or something like that. System value, or I can't remember. But it was all one thing, which is why you see 1, 2, 3, 4, 5, and then decision quality picks up at 6. That's why decision quality starts at 6, because it used to all be part of the same thing. And what I realized was it was 2 different things. And I found that by essentially seeing that they were separating into 2 separate groups. So that was easy to justify because there was a clear separation conceptually. If it is erroneous, if these items here are all like totally conceptually unrelated, but statistically, miraculously correlated, it's just a statistical anomaly and you shouldn't keep the factor. It's just an anomaly. Yeah. But if they are all related, maybe use it. You learned something. Okay.
Did you save your final EFA to the shared drive?
No, I didn't. Would you like me to copy the pattern matrix or the output file, or? Yeah, okay.
Yes, please.
Yes, all right, I'll do that. Let me see, let me copy this and I'll save it to a Word doc. Oh, I did, there it is, but I didn't stick it on the file. So let me just save this to the folder there. Bootcamp, nope, that's not the one. Google Drive, where'd you go? There's Google Drive. And so many things. Let's see, bootcamp. Where would I even stick it? How about I stick it just in the main folder? 2019 final pattern matrix. There we go. Cool. Also save the output file just in case. Let's see, save as, not here. Drive, where'd you go, where'd you go, where'd you go? There we go. Okay, and I'll put this in data. Okay, final output file SPSS 2019. Cool, so that's available as well. Did you know you can export this as a PDF or as a website? You can interactive website. Yeah, check this out. It's pretty cool. File, export as web report. Yeah, I'll just stick it there in that data folder, save, and check this out. It becomes interactive, linkable, searchable, copyable. It's thinking. It's a lot of stuff. You can also export it as a PDF. Eventually. Wow, it's taking longer than I expected. Well, while that's going, back to here. Okay, number 1 rule of exploratory factor analysis. Exploratory factor analysis assumes that all the items are part of reflective latent factors, that they're tightly correlated within each factor, conceptually. So don't include formative measures, don't include single item constructs. Like if you're measuring revenue, don't throw revenue in there. That's a single item thing. It's not going to be tightly correlated with anything unless you're also capturing measures that are related to revenue. Yeah, don't throw categorical variables like gender in there. That doesn't make sense. We should talk about reflective and formative. Oh, did I stick in? I'm going to actually take you elsewhere for this. I'm creating a course, an SEM course with assignments and tests and yeah, available online to anyone. I'm so close. I just had so many other things going on this semester. Structural equation modeling, there we go. And in it, I'm creating better videos, better visuals, and there we go. Oh, it's over here. Assumptions, here we go. I created over 20 new videos just for this course. Here we go. So, formative and reflective factors are a lot like bread. Reflective indicators are just slices of the bread. They're all the same, just different slices. It's like our usefulness questions that ask the exact same thing, just in different words. Those are reflective. Formative, just totally different dimensions of the factors. Still all ingredients of the bread, right? But if you were to remove one of those ingredients, one of those dimensions, it changes the thing you're creating. And so, like if we took out the eggs, it would be some pretty flat bread, right? We took out the yeast, super flat bread. Took out the oil, that'd be horrible. So the nature of the construct is determined by its dimensions, its various ingredients. Whereas reflective, they're all just a reflection of the main construct itself. So for example, right here, a reflective set of measures. I'm very satisfied with my job. I love my job. I enjoy my work tasks. No rational person would answer strongly agree to one and then like strongly disagree to another one. If you're very satisfied with your job, you would not say, I hate my job. That doesn't make any sense. Whereas formative, there's no requirement for these to be related. So the software is useful. The software is easy to use. I'm satisfied with the software. Those are three totally different things. I can have software that's useful that is not easy to use. For example, Amos, SPSS. Those are useful, but not very easy to use. I'm satisfied with the software. That might be a totally different aspect of whether it's useful or easy to use. It might be both of those, but you're not very satisfied with it. Who knows? You might have different expectations. So none of these have to be correlated, although they might be correlated. You might have software that's both easy and useful and satisfying. That could happen, but it's not required. So these are formative. You take out one of these, and the nature of the thing you're measuring also changes. So that's formative versus reflective, and an EFA expects reflective. CFA, we can fiddle with it a little bit, not in Amos, but in other software. But in EFA, it expects reflective because it's based on the covariance matrix, which implies correlation. Okay. I hear someone on here. Did somebody have a question remotely, or you just forget to turn off your mic? There we go. I muted you. Okay. Hopefully you weren't saying, yes, I have a question. Mute. Okay. There we go. So that's formative and reflective. Here's another example. I eat healthy food. I don't eat much junk food. I have a balanced diet. Those things all move together. Nobody's going to answer one strongly disagree and another strongly agree. Whereas health, I have a balanced diet. I exercise regularly. I get sufficient sleep each night. These are totally different things. You might exercise but get terrible sleep. Or you might eat well but never exercise. Or, you know, several of us can find ourselves answering one or two of these, hopefully, correctly or positively, and another one negatively. So very formative. But those things all combined would indicate a healthy lifestyle. So there is a common construct. It's just formatively generated. So you tell me, formative or reflective? Definitely reflective. No one's going to rationally answer these differently. Formative or reflective? I just gave you this one on the website, sorry. Yeah, that's formative. All right, here's a new one. This one's tricky. Yeah, it's formative. It's probably a higher order factor. You can see there are little dimensions in here. Like 1 and 2 are a single dimension. 3 and 4, they're a single dimension. 5 and 6 are single dimension. So you have a 3-dimensional, probably higher order factor, which we'll talk about in a moment. How about this one? Yeah, this is reflective. These are all the same thing. Very important. That's one reason EFAs fail. I get emails about this all the time. Why did my EFA fail? How can I fix it? Well, you have formative factors. You can't do an EFA. So there you go. All right. Let's see. What if you do have formative measures and you want to do an EFA and you want to do a factor analysis? Well, you can't do an EFA, but you could do a CFA with PLS software, partial least squares. For those who are interested, I'm going to cover this on Saturday after lunch, probably. And those who aren't interested in PLS, you're welcome to go. But PLS can handle formative factors in a factor analysis. You can also just simplify. If you don't want to use a partial least square software, create a summative score. Sum up your items or average them. You can even weight them if you want, and just create a single measure, and then just skip factor analysis, go straight to causal analysis. Like start with your regressions. And as long as you don't have a latent factor, it's fine. So, for example, with these guys here, the software is easy to use and useful and satisfying. I could just average these scores and say, this implies software satisfaction. It's one thing, this new average. I'll use that in my regressions. The thing I'm going to predict is this one new average. Okay. One question I get now and then is, what do I do if I have a small sample size? Can I do a factor analysis? The answer is yeah, you can do factor analysis with small sample size. But if you have like too little, like if you had, let's say you have 50 variables, like we had almost 50 variables. What would be too small to be running a factor analysis with that? Usually about 3x. So with ours, what do we have? It was a 37, I think, or 47. We had 47. Let's call it 50. If we had less than 150 sample size, it'd be really hard to run an EFA on all of those variables. We might have to split it up into just, first half, second half variables, or something like that. EFA doesn't require normality, although it's helpful. Talked about that. Here's the KMO. Remember I said anything above 0.8 is pretty good. Below 0.6 is pretty scary. These are the actual names, labels from the publication, Kaiser and Rice, 74. That's what they called them. They got away with it. So that's cool. Just reminders, extraction methods, which we talked about. These are the three main ones. And why you might use one over another, but really they're just a tool. Rotations we talked about. If you end up in your pattern matrix, if you end up with a Haywood case, which is a loading greater than 1, you'll want to go with Varimax rotation. What this does is it suppresses a little bit. It pushes down super extreme loadings. So yeah, that'll work for Haywood cases. Here's the quote itself. Hare says, different extraction methods arrive at essentially identical results. No compelling analytical reason suggests favoring one rotational method over another. So if somebody asks you, why'd you use Promax or why'd you use maximum likelihood? You're like, well, because Hare says it's just a tool. So I can use whatever I want. And Hare's the boss. This guy's been cited like 48,000 times. So if he says it's okay, it must be okay. All right. Talked about that. Talked about that. Talked about that. Talked about. I didn't show you that. Real quick, scree plot. Let me show you a scree plot. In SPSS, if you run a factor analysis, you can also choose a visual representation of your eigenvalues. That's over here in the extraction button. If you go to scree plot, I'm also going to push this back to principal components. But if you go to scree plot, it will visually graph your eigenvalues right here. And typically, where there's an elbow, now we don't have an elbow because we have so many variables, but typically where you see the elbow, which is about here, that's where you end up cutting off, adding more factors. Because you can see every additional factor adds very little eigenvalue. So we stop there. 1, 2, 3, 4, 5, 6, 7, 8. That is correct. So we cut it right there. You ever report that? Yeah, in your dissertation. Nobody else cares. And they don't care about your dissertation either. Sorry to break it to you. You'll work so hard on that. Those of you who haven't done it yet. You'll be the one who reads it. All right. Funny story, 2 seconds. There was this guy in our department who was notorious for being absent-minded and not showing up to his students' dissertation defenses and not reading his students' dissertations. And he showed up to mine, having read the entire thing, marked it up. I had a 360-page dissertation. He marked it all up in red. He's like, I'm ready. I'm like, what are you doing here? You're not even on my committee. He was so upset. So we added him, honorary committee member. But yeah, I don't know what he was, anyway, trying to make up for past sins. I don't know. Poor guy. He liked it. Okay. So that was good. At least he didn't have like negative comments, and he's not on my committee. That would be terrible. Okay, here we go. We talked about that. Oh, this is important. Statistically speaking, there is a threshold of adequate loading. And I said 0.5. Anything less than 0.5 and you're wasting your time. But according to the statistics, strictly speaking, it really depends on sample size. But practically speaking, you still have to compute an AVE, which is the average loading, essentially. And so if you have low loadings, your AVE is going to be low. And you're not going to pass your criteria for convergent validity, which would be a 0.5 in the AVE. So even though you can justify having the low loading by a higher sample size, practically speaking, you're still sunk if you have low loadings. But if you want to keep one, there's your justification. Okay. Adequacy. There are 4 things you want with an EFA: adequacy of correlations, discriminant validity, convergent validity, and reliability. So adequacy is measured in this way, with the KMO greater than 8 and communalities ideally greater than 0.5, but it can be as low as 0.25. And I kept, didn't we keep one of them that was like 0.12 something? Yeah, it's fine. It's a tool. And then total variance explained, ideally greater than 0.6, but definitely greater than 0.5. That's your adequacy. And I would report this in your write-up. The adequacy of the correlation of items in the EFA was this stuff. Validity, you got convergent, discriminant. We talked about both. Convergence is high loadings on a single factor, and discriminance is staying on that factor and not loading on other factors. In this example here, you can see loyalty 8 is loading on multiple factors. There's a discriminant validity issue there. You might also see here, look at loyalty 4. It's loading on multiple factors, but look at the difference between those loadings. It's clearly loading on factor 5, not on factor 4. The difference between the primary and secondary loading is really big. The published threshold for that difference is 0.1. I strongly recommend 0.2 as your difference, but 0.1 is the acceptable threshold. So if the loading for loyalty 4 on factor 4 was 0.600, technically you'd still be okay. Practically speaking, you might have some trouble. There was a question remotely, let's see. Question: for a dissertation in social science or business, what is your suggested sample size? I've seen conflicting literature. Yes, there's quite a bit of conflicting literature. My dissertation chair is not to worry about sample size, the actual testing of the theoretical model. Check it out. I have written, where did I put it? Here, SEM criteria. I'm writing a massive paper right now. All the validity criteria for SEM. It's a beast. But in there, I have sample size recommendations. And it is, did I include a master table? Oh, I have the table elsewhere. Dang. I'll just do sample size. Sample size. Nope. Here we go. Sample size adequacy right here. Here we go. Here's my recommendation for sample size. You can have conservative, moderate, or liberal approaches. Conservative would be bigger sample size, 50 plus 8 times the number of questions in your survey, or the number of questions you think you'll carry over into your structural model. So in our case, in fact, here are some examples here. Let's say you had 40 variables. On the high end, you're going to need about 370 for your sample size. On the low end, you'll need about 170, which would be 50 plus 3x. So yeah, there's quite a range, and there's literature out there to support all of it. So the point is you want to minimize error sufficiently so that you can run reliable estimates. If the estimates you're calculating have a lot of error involved due to low sample size, then adding 1 or 2 additional data points might change your results drastically. And so that's what you want to avoid. You want to have enough sample that you're robust to additional or less sample. Can you get that paper? No, not yet. What was the question?
When you write 40 variables, do you mean 40 variables in the same model that you're using for the analysis, and not 40 variables in the data set, yes?
Correct, yeah, 40 variables that you plan on using for your model.
Okay, great.
Yeah, you might have 1,000 variables in your data set, but if you're only using 40, then that's where you calculate your sample size.
I have another question regarding to the factor analysis.
Okay.
If I am translating a scale, let's say from English to another language, what other than factor analysis and reliability do I need to include before publishing such a thing?
Oh, okay. So if you're, the part maybe I don't understand is so you're translating from a different language. Does that mean you need to do any additional analyses? Is that what you're asking?
I have 2 different samples using the scale, the translated scale.
Ah, okay. This is a good question. Yes. Yeah. If you have 2 different samples using one language and another language, then you need to do what's called a Levene's homogeneity of variance test. This is relevant to multiple people, so I'll just show you.
The 2 samples that I have actually use the same translated scale, like the new language.
They use the same language?
Yes.
Oh, so what's your question?
What should I do next?
So you have you have 2 samples. Are they collected at different times? Is that what's going on?
Yes.
Ah.
Different populations, different times, but the same translated scale.
The translation has nothing to do with what we're talking about. Okay, so
just answer what you wanted to answer, and maybe
so the answer is actually going to be the same. So you have multiple samples, and you want to make sure that they are measurement-wise the same, right?
Yes.
Good. Okay. Cool. So again, you just do the homogeneity of variance test, which is in SPSS. Let me show you. What you do is you'd run an ANOVA. Let's pretend, for example, that we'll just do this with gender because I have it. Let's pretend gender is 2 different populations. Maybe it's maybe I collected data from Japanese folks and from Chinese folks, 2 totally different populations. And I want to make sure the measurement is equivalent across those 2 groups. I would do analyze, compare means, ANOVA, and inside the options, I would check the box for homogeneity of variance right here. So options, homogeneity of variance test. This is a Levene's test. And what this does is it checks to see if there's consistency between the groups when it comes to the measurement variance of each item. So I uncheck the means plot here, so I'm not doing that. Hit continue. And you would do this for all of your measurement items. So for me, that's everything from useful 7 down here, all the way up to anxiety 1. Stick that in here, and then hit OK. Oh, not child order, it's gender. And this will tell us if those groups are the same or different on each item. Oh, have I split my data? I wonder if I split my data. No, here it is. Okay. So the result here in the test for homogeneity of variance, you want to look at the SIG column, and any value in the SIG column, any p-value less than 0.0, well, depending on your threshold, 5 or 1. I usually take a stricter approach here and do 0.01. Anything less than 0.01, you would say, oh, that is different across groups. They measured it differently, or they understood the question on the survey differently across these two groups. And so you can see there are a few of them based on mean, based on median, and you can choose which one. I would just do based on mean for all of these, and you can see most of them are fine. In fact, all of them are fine based on mean. But if you had one that was significantly different, let's say, for example, this social desirability 3 was significantly different between the two groups based on mean, you would check to see if the other items on that construct are also significantly different. If they are not, then you're fine. You can keep going. Carry on as if it's one sample. If more than if the majority of items on a factor are significantly different in a homogeneity of variance test, then you have a problem, and you cannot use those two samples as if they were one sample if you can use that variable. So you can remove that variable if you want, or just treat the two samples as two different samples.
This is for measurement and variance.
At the EFA level, measurement and variance. We're gonna do it again in the CFA. Yeah. But it's essentially the same thing. Yeah. This would be, the Levine's test would be like a metric in variance. It's not identical, but it's similar. Yeah. Cool.
If I understood her question, really interesting question to think that understanding two different languages or two different, the question given to people that had two different languages that are taking the same survey, how you manipulate that in the program.
Right. So if I understood correctly, she had two different samples, two different countries, but same translation of survey. So maybe they understood it differently, though, based on their.
That's what I thought you were referring to.
And that's sort of, yeah, I'm not positive I got that right. But what we're determining here with the Levine's test is, did they interpret the questions similarly and respond with similar distributions? Yeah.
Can you do that test with more than just two samples?
Yeah. Since it's an ANOVA, you can do it with as many as you want.
The original scale is written in English and used in English-speaking populations.
Oh, okay.
But I have translated it into a different language, and then I conducted two different studies in two different times with two different populations, but with the same translated, new translated survey.
Right, and were the two different samples, were they speaking different languages themselves?
I just translated into Arabic.
Okay.
So it's one language that I from English to Arabic, and then conducted in two different countries that speak Arabic.
Oh, so they both spoke Arabic.
Yes, but two different samples, different populations, everything is different.
Yeah, so if you have a good reason, a theoretical reason for why these samples might be different, then you'll want to conduct a Levine's test, like I just showed, just to show that they are equivalent when it comes to measurement.
But how do I say that the translation of the survey, I
don't know that the translation has anything to do with it. Because it was just one, it was all in the same language. So statistically, I don't think the translation is, I don't think there is a statistical assessment that needs to go into addressing the language translation, since it was all one language.
So how do you validate a scale that is translated?
The way you validate a scale that is translated is the same way you validate a scale in any language. Our scales here could be in Farsi, and we would use the same statistics.
But it will include reliability and
Oh yeah, definitely do the EFA, do the reliability, Cronbach's alpha.
factor analysis, all that.
Yep, all of it. Everything we just did, do that no matter what language it's in.
But you compare it to the original scale. To the loading of the factors in the original scale.
You mean like the English-based scale?
Yeah.
If you had data for that, yeah, you could do that if you wanted. You mean like somebody else's data?
Yeah, so just compare the original like author who wrote about
Oh, from the original author. Oh, okay. Yeah, statistically, yeah, what you would do is compare their Cronbach's alphas.
Okay.
Yeah.
Okay. Thank you.
You're welcome. Okay. Let's do this. Let's take a 5-minute break, and we'll get back to it. Yeah, in 5 minutes. Remote folks, I'm going to pause the recording. Here we go. Remind me to resume recording when we get back. We're doing pretty good for time. We have 1 hour left, which is fabulous. We might actually be ahead of things. We talked about convergent validity, discriminant validity, reliability. In EFA, we use Cronbach's alpha. In the CFA, we use composite reliability, which is a slightly updated error accounting for error term, error measure. So it's a little bit better. Let's see. There is a grand flow of EFA. If you get lost, because you can do an EFA forever. Literally, I mean, you can infinitely iterate. Every time you add a variable, change a parameter, change a constraint, the thing changes. And you have so many variables. If you do the math, the permutations actually end up being, you could be there for a decade doing one EFA. And I've had people say, I've done this EFA inside and out for a month, and I can't figure it out. So there is an order of operations that I've been wanting for 8 years to write a plugin to automate the EFA. And so I finally sat down with the research assistant, and he said, well, what is your order of operations in your head? What are the lists of heuristics and order of those heuristics? And we wrote it out. We created a flow diagram, and we figured it out. And it was actually a lot simpler than I thought it was. It was just all in my head, and it's all human judgment, but it's not really. There's very specific guidelines and rules and order of things. So here's the order. And I don't think I'll go through it, but we just did it. And this is it written down for you with thresholds and in order how you're going to do it, and looping through, iterating through different criteria until you meet a certain threshold. So for example, if the KMO is less than 0.7, then stop, because you have the wrong set of variables. If you pass that check, then you move on to discriminant validity. You just go check the pattern matrix. If there are cross loadings that have differences less than 0.2, meaning your primary and secondary loading are really close to each other, well then start deleting things, starting with the lowest difference. Oh, go for it. You have these slides too. They're on the, yeah, these slides are on the Google Drive. Yeah. And then after you've assessed iteratively discriminant validity, if you've got it figured out, then you jump on to convergent validity and figure that out.
Can you say assessed or obsessed?
Yes.
Okay. I have a problem with the latter.
EFA is easy to obsess over. You can go on forever with an EFA. So we actually wrote a plugin for this, and it works, but only for very clean data. So we're working through the bugs right now. I haven't released the plugin yet, but it works. And so with the first time we tried it, we logged all of the EFAs it tried in order to get to the ideal EFA solution. It was something like 500. And so it recorded all of them, and it took about 30 seconds. And yeah, and then it reported, here's the one you should probably go with, and here's why. and gave you the reasons and all the things it did. Here's the item I deleted and why I deleted it, and reported all that as well. So I'm hoping to have that out soon.
How do you objectively judge the best EFA?
There are different ways you can do it based on the total variance explained. That'd be a really good way. The quality of the factors, if they have low loadings or high loadings, and if there's discriminants between them. And then the correlation matrix, if there are no great correlations, like above 0.7.
And none of those work in contrast to the others. It would just seem like you're always going to be making trade-offs. Or not.
Turns out, yeah, there are a few trade-offs, but you can do them programmatically. And so that's what we've done. Anyway, he's at an internship right now. So I gotta wait for him to get back. Or I could just write it myself, I guess. But that's what students are for. Do the grunt work. Okay. Anyway, that's exciting. Caveats. If you have a higher order construct, a multi-dimensional, remember, escape, if we go up here, oh, why isn't it? Hello? There we go. This red one here, we had 3 different dimensions, each comprised of 2 items, three dimensions, 2 items, each dimension, and there's this higher order construct. So really it's, it doesn't look like that. Do I have a visual of this? I should have created a visual. What it looks like is something like this. You have a factor that has factors. Has 3 factors. And each of those factors has its own dimensions. Whoop, like that. And each one has 2 dimensions. Like that. And so this factor is comprised of 3 different dimensions. Each one of these dimensions has its own individual items that are used to measure it. When you have a factor like this, you shouldn't include it with all the other factors. You should have it do its own EFA, because otherwise these underlying dimensions, their items, these 2 and those 2 and those 2, they're gonna collapse together into a single factor, which will look wrong in your EFA. You expect them to separate. So do a separate EFA with those, and that will work better. Sort of like what we did with social desirability. Down here, talked about that, and here we go. Talked about that, and that, and that. Yeah, good, we talked about all that. Woo! Here are videos. If you get lost, not only is there this video that I'm recording right now, but there are all these videos that talk about the EFA and the process of doing that. So you'll be covered. Other things we can do in EFA, we talked about that. What would you record? Here's the, man, I need to make a document on that. What do you actually report from an EFA? You report these 4 things: adequacy, reliability, conversion, discriminability, and your evidence for them. How much do you report? In your dissertation, you report a whole section, pages and pages. In a journal article, a paragraph for the whole thing altogether. And then maybe stick your pattern matrix in the appendix. That's what I would do. Because nobody wants to see more than that. But in your dissertation, again, go all out. Put all the details in there. Extra time. We talked about saving factor scores. Second order factors we talked about. Ooh. Cluster analysis. EFA. Okay, so the things we can do with the remaining 53 minutes. I could, every time I do one of these, some student comes in who's been struggling over their data in an EFA, and I just do it for them. And they love me for it. It's great. They named their firstborn after me. Is anyone in that position this year that they have data and they're like, I hate my EFA?
I could promise my 7th grandchild.
Not your firstborn? All right. Legal name change. Does anyone have data that they're in that position? If not, we're cool. You do? You have data that needs to be EFA'd?
Well, I have the data. It's in a revise and resubmit.
Oh, okay. So you've already done it.
Yeah, I've already done it. But what I did was in the revision, this is based on our conversation, we can have it go or whatever, is I took my factor analysis and moved it to the appendix.
Oh, okay.
In fact, I'm glad you said that because that's what I thought. It was just getting
Too much
room,
yeah.
too much detail. And so what I've done is the factor analysis is not absolutely central to my model now, which I'm fine with. But I'd be happy if you wanted data. I'd be happy to.
Looks like these remote folks are gnawing at the bit here.
Okay.
I've got data. I've got data. So if you've already done yours, let's see. I have data. So Naveen, Raphael. Raphael. All right. Why don't you both send me your data and see what we can do? I sent it in the morning, actually. Okay. Maybe I missed it. All right, I'm going to blank my screen so it's not recording my emails. Give me a sec. Let's see. Pause, share. There we go. You guys can see my emails. Oh, Naveen. No, that's not the right Naveen. I know too many Naveens. Okay. Naveen, I don't see, let's see. Oh, Raphael sent it in the morning. Raphael, I don't see yours. Oh, unless it might be in my stats support box. Let me go here. AR, nope. Oh, Raphael, here we go. Here's your data. Cool. Oh, you were prepping for this. You were hoping for it. All right, let's try it. So, okay, I have Raphael's data. And he sent me everything. Oh, this is beautiful. Thank you. Okay, I'm going to do yours. Naveen, if we get to yours, also awesome. But I'm going to start with Raphael's because he sent me everything I need. Okay. And then just to make sure I don't miss anything else, was anyone like desperately hoping for cluster analysis? Okay, great. Good to know. They use a lot in marketing. So if you're in marketing, it's a good thing to know. But I have tons of videos on it. Feel free to watch those videos. Okay, this is gonna be fun. It's always a challenge. There's nothing up my sleeves. I've never seen this data before.
Are we going to have a chance to do this too?
Do his data?
Yeah.
Oh, I don't know. It's his data. Probably not. No, just watch. Okay. So put him. You guys aren't allowed. Yeah. All right. Let's see. Okay. Here we go. So here's the data. I'm going to open it up in SPSS. Let me pull it over to SPSS. For converting Excel to SPSS, all you do is drag the file into an SPSS window, and it starts to read it. It says, here's what I see. Is this right? You say yes, and it produces the data for you. Problem is, it will say everything is nominal. Let me go look at it real quick. These are all numbers. Good. Raphael, I might need you to jump on the mic and just walk me through here and there. Looks like I have gender, age. These are all Likert 1 to 5, it appears.
Yeah, that's right.
That's right. And let me see if I can
I can't
push.
see your screen yet, though.
Oh, I'm sorry. Stop. Let me resume sharing. Sorry. Okay. Also, I'm going to see if I can push this out. All right, Raphael, will you say something else again real quick?
Sure.
Oh, yes! I have you on the speakers. You are now the voice of God. Okay. Let me make sure the volume's up enough. All right, I now have you so everybody can hear you. Woohoo! Should have done that from the beginning. Okay. Yeah, it's just the first day. Okay, so Raphael, it looks like everything from data share to the end is 5-point Likert scale. Is that right?
Yes, everything is 5-point Likert scale.
Cool, except age and gender, I guess, but that's no problem. Okay, so then,
Yeah, exactly.
Are all of these included in the EFA?
Yes.
All right, let's do this thing. Okay. Control A, accept you. Oh, it thinks they're all nominal. Let's see if it'll run anyway. Let's see, get rid of this one and this one. Okay, and let's do, now, Rafael, do you think these are all reflective?
Yes, I think so.
All right, we shall find out. Once you've done a few of these, you would start moving really fast. Let me not save the scores. Good. Okay, and let's run. So right off the bat, we have a KMO of 0.8, which is fine. We look at our communalities; they're looking pretty good. They're looking really good, actually. Look at our total variance explained, and we have 71%. Holy cow, that's really good. Let's scroll down, skip this table, skip this table. It's the produced, and we have 23% non-redundant residuals. That's a lot, but it's less than 50%. But here's the pattern matrix, what we're really hoping for. Let me zoom out so we can get a rough picture. Ah, quite a mess. All right, fun is right. I eat this stuff up, I love it. Okay, so we clearly have some issues. Let's do this. When I have a really messy data set, I like to do this that I haven't shown you, which is options and sort by size. That's going to just clump them in order by biggest to smallest, and it sort of makes it easier to process. So let's do that, zoom out, and hit OK, jump straight down to the pattern matrix, and here we go, sorted by size. It looks like there's some things that are loading together. Now you sent me, I think, a data sheet, so let me go grab that. Oh, sorry. All right, so here's the data sheet. Here's the wording, excellent, thank you. Oh, this is great. Okay, not even that big. So let me go back over to here, and we see we have, what is FAC-COND? That is
facilitating conditions.
Facilitating conditions. All right. Facilitating conditions seems to go with effort expectancy. Those are tightly related. Yikes. That's all right. We'll look at that in a sec. Then EXP, is that experience?
Expectation.
Expectation. Falls with INT, which is intent.
INT is intention.
Okay. Performance expectation is here, and oh, that's effort up there. Let's see, cost. Oh man, this is such a mess. This is great. Okay. VIS risk seems to have some reliability here. Good. Cost, 1 and 2. Were there more costs, or is it just the 1 and 2? Looks like just those two.
There are 3.
There are 3.
Up front.
Oh, right up here. Dang, that's unfortunate. Okay. And data sharing concerns.
Wow.
That is all over the place. All right, let's do something real quick. Let's have some fun. How many factors do we expect? Let's start there. We expect 1, 2, 3, 4, 5, 6, 7, 8. We ended up with 10. Let's just try to force it to 8, see what happens. Hit OK, hit OK. See what it looks like. It's probably still going to be awful. Yeah, it's still awful. That's all right. Let me try this. Let's jump over to maximum likelihood. See if that makes it any better. Just doing sort of these brush broad strokes. How about that? That's looking better, but is it better? Let's see. Facilitating conditions and effort expectations still in there, but those are better. Those are better. Cost 3 is still an issue, but that's better. Data sharing concerns. Oh, but we have a ton of those. We have some wiggle room. Good. I should show you, as I'm doing this, I should show you real quick. If you were to go to the StatWiki and look at the citing claims link, that's kind of new. I added, there's this one, 4 indicators per factor. Turns out, so there's an ideal number of indicators per reflective factor. It's 4. This is a published thing. Any more than 4, and you probably end up having multiple dimensions. Any less than 4, and it's hard to minimize error and converge. So 4 is the ideal. So we have plenty of room to wiggle with some of these, like viz risk and data sharing. So what I'm going to do is I'm going to reduce some of these. And I'm going to start with start up top. Here we go. Facilitating conditions and effort expectancy. I'm going to put all of those into a single EFA. There's and get rid of everything, and just put back. It was facilitating conditions and effort. Here's effort. Put that in. And facilitating conditions. First thing I want to do, I want to look at the wording. Over here. Facilitating conditions, right here. Let me zoom in. I have the resources necessary to use the system. I have the knowledge necessary to use the system. I have control over using the system. Given the resources, opportunities, and knowledge it takes to use the system, it would be easy for me to use the system. Oh, that's a little different. Number 4 might fall out. Then effort expectancy. My interaction with the system would be clear and understandable. It would be easy for me to become skillful. I would find the system easy to use. Oh, well, there's a problem. Those are the same question. Look at that. This one and number 4. It would be easy to use the system. Easy to use the system. Oh, that's why they're, look at it. The number 4 is the same. Ah! So, well, that's a problem. So that's why they're overlapping. So let's just pretend that we don't have a problem for a second. I'm going to do it based on eigenvalues. I'm going to principal axis factor this thing and hit OK. And yep, we end up with 1 factor. So let's push it out. Let's try real quick for principal components analysis and see if it pushes it. Nope, still 1 factor. So I'm going to force it. Oop, not ANOVA. I'm going to force it to 2 factors and see where the cross loadings are. Continue, okay, and we jump down to the pattern matrix, which is right here. Okay, zoom in. Facilitating conditions 4 and 2. You know what we need to do? Check this out. Go to rotation and show the loadings plot. Continue, continue, and jump down to the plot right here. Here we go. Well, that's a mess. So facilitating conditions 1 is way over here. And then looks like facilitating conditions 4 is bridging all of this. So let me get rid of facilitating conditions 4 and see what happens. And try that. And pattern matrix, where'd you go? Oh, there's the pattern matrix right there. And it's a little better, but facilitating conditions 2 is still loading over there. If we look at this right here, here's facilitating conditions 2. Let's do this. I'm going to lop off actually number 1. You may say, James, you're crazy. But it's not loading together with number 2 and 3. So let's lop that off and see what happens. And we might even stick 4 back in. Let me stick 4 back in. And worse. Yep, 4 is still loading on both, so let's look at the plot here. Yeah, 4 is still just right in the center of those. So, last try here. Now, we now have only 2 items on facilitating conditions. That's troublesome, right? Now these cross load. We look at this. This one here is pulling them together. Last try. That's number effort expectancy 4. And these are all the ones that are easy to use, right? All those ones that we said we read had the easy to use language. Now they're separated. That's good. And they've separated here. That's good. And their eigenvalues are not above 1 for the second one, unfortunately. So these will still collapse together. So at this point, I would say, these aren't truly different things. They're asking about the same thing. And you may say, well, no, Dr. Gaskin, somebody already published this. Well, they were morons. What were they thinking? Putting ease of use on 2 different dimensions. That doesn't make any sense. Why did they do that? So I would fight against it. And I'd say that one of these things is not helpful. It's redundant. So let's take that approach. And your advisor may say, no, this has been published, you can't do that. Tell them to talk to me. I'll talk them out of it. Okay, so let's put all this back, put all this back, and get rid of, which one do you want to get rid of, Raphael?
So out of the 2 constructs, like removing the whole
Yeah, the whole thing, effort expectancy or facilitating conditions.
No, facilitating conditions.
You know, I'm totally with you. Yep. I would have chosen that one as well. Okay. Sorry that hurts. Okay. Based on eigenvalues, let's try again. Let's not look at the loadings plot because the loadings plot of 9 dimensions is not humanly comprehensible. Okay. Scroll down. Okay. And we get to expectations and intentions. Oh man. That's really overlapping. Okay, let's keep looking here. Wow, data sharing concerns splits into multiple dimensions, like a lot. Let's look at that before I address those other issues. Data sharing concerns. Where'd you go? This one. I would not mind if external entities learnt about my store. I would not like it if external entities took advantage of my information. Those are 2 different things. I would be concerned about the potential misuse of my data by external entities. That's reverse coded. The system should enable me to choose which data I'm willing to share. That's also something different. I would feel uncertain capturing data about my business in the system as they may be accessed by external entities. All right, so that goes with, is it 3, 2, one of those 2? The system should guarantee the privacy of my data. The system should allow me to decide who has access to my data. I would not mind sharing data about my store. Okay, so there are multiple dimensions in here. This is like my red box from the slides, where there are multiple dimensions. So before we stick this in with everything else, we should assess it separately. So let me get rid of all this and just look at this by itself. 3 dimensions came out. And mostly clean, mostly overlapping, and we have that there. So it looks like there might be 4. I just skimmed over it here, but if you see this eigenvalue in 0.988, there might be 4 factors there. So let's force this out to 4, or better yet, let's just try a different factoring method. Use principal axis factoring. And it says 3 still, but how's it look? Still a mess. Try maximum likelihood. Still 3, but not a mess. Okay. Data sharing 5 isn't loading anywhere. Data sharing 8 isn't loading anywhere. They're low loadings. So what you might do, Raphael, is you might pick which dimensions you're actually interested in. Another approach we could take, is go like this. Do a reliability analysis, just throw data sharing in there, and check this box over here for scale of item deleted. And that'll tell us what will the Cronbach's alpha be if I delete an item. So right now the Cronbach's alpha is really low. Really low, 0.53, move 7. Too low. So if I look over here, if I were to delete number 8 here, we jump up to 597. So let's delete number 8 and see what happens. We run it again, scroll down, and we look. Sure enough, we're at 597. We look at this and we say, oh, what could we do to improve it? Delete number 1. We'd be up to 643. Okay, let's try that. You may say, it looks like you're fishing. The answer is no, I'm creating a reliable construct. You want reliable statistics, you need reliable constructs. Okay, 643 is where we're at. Can we get above 643? The answer is no. Which tells me that this is truly multidimensional, which means it is formative, which means it doesn't belong in an EFA. So for now, I would just leave it out of the EFA. And what are you going to do with it? Well, you could model this in a partially square software like PLS, or you could create some sort of index or summative score for it. Let's take out facilitating conditions again. And we run this. And we look. All right. So we're getting closer. Effort expectation and performance expectation. Yeah, I can see why those might load together. Let's go look at the wording. Performance expectancy. I would find the system useful in my job. Using the system enables me to accomplish tasks more quickly. Using the system increases my productivity. Using the system will improve my performance. Good and reflective. Effort. My interaction with the system would be clear and understandable. It would be easy for me to become skillful. I would find the system easy to use. Learning to operate the system is easy for me. You can see why these overlap, yeah? Becoming skillful with it, increasing your productivity, very similar. Easy to use, improve my job performance. They are different things. They are not the same thing. They should be separable. Let's find out if we can separate them using a different factoring method. We did. Yay. Okay. Did we? We did. They just went all over the place though. So more problems. Expectation and intention. Let's jump to those. Check this real quick. Oh, what is the link to the StatWiki? Just Google StatWiki. You'll find me. Am I sharing my screen? I am now. Yes. Okay. Okay. Expectations and intentions. Go with those wordings. Right here. Intention is, I intend to use the system within a year from today. I predict I would use the system a year from today. I plan to use the system a year from today. Those are all pretty similar. And then expectation, I expect to adopt the system within a year from today. These are the same thing. I will adopt the system within a year from today. These are the same. Your behavioral intention and your behavioral expectation and your behavioral intention are exactly the same. Do you prefer to keep one or the other?
Yeah. Yeah, maybe intention. Although, so the thing is, I found this in the literature, and there are even papers talking about why they are different and things like this. So, yeah. But also, since I looked at them in the literature, I thought they were very similar, but they made a lot of sense theory-wise. So that's why I used them.
They are, yeah, they're very, very similar. I would be hesitant to use them both in a model because you'd be facing tautology, predicting something with itself, which would inflate your R-square and inflate all your effects. So with that in mind, just playing around here, you don't have to keep whatever I do. But if it were me and if this were my data, I would drop this one. Whoops. Drop effort expectation. Was that the one? No, not effort. Behavior.
Yeah, yeah. No,
Behavior.
I think it's okay.
Which is down here, EXP 1 through 4. Okay, we run that. If nothing else, we're learning. what makes a good set of data. Okay, effort expectation loads with intention. Got to go look at that crossover. Effort expectation, that's the one I can become skillful, right? Let's see. Clear and understandable, easy for me to use, operate it. Okay, so what's going on here is there's just a general lurking variable of essentially positive attitude towards the system. It's floating both of those. So we can try to separate them. We'll get back to that. Performance expectancy. That's separating somewhat, except it moves with cost. Okay, let's go. I'm actually just going to drop cost 3 because it's not even close to loading with its other 2 cost ones. So cost 3, you're gone. Jump back down. Viz risk. There are 2 different dimensions to viz risk. I'm going to drop the second dimension, which is 1 and 4 over here, because we have lots of items over here. I'm not even going to look at the wording, because we have so many and so much to do here. Viz risk 1 and 4. Okay, jump down. Viz risk is now pretty clean. Cost is clean. Perf with viz risk 7. Let me drop viz risk 7. Because it's cross-loading with perf. All right, perf now looks pretty good, except maybe this one, we'll see. Viz risk is clean, cost is clean. So now we're just left to these ones, effort, expectancy, and intention. We're gonna try a different factoring method, see if it helps. I kind of doubt it. Okay. Down, pattern matrix. Actually, that did change things up. Wow. But now perf and cost are loading together. All right, let's try one more factoring method. Oops, this one. And they're back. Okay. All right, so what do you do here? Let's go look at performance expectation, because we haven't looked at that one yet. Well, here's cost. Do we need performance and effort? Here's effort, expectancy. These 2 right here. Didn't we just look at those?
Yeah.
All right. I thought we took one of those out. Easy to use, increase my productivity. No, they are clearly different. They're just both highly correlated. So let's try one more thing here. I see 4 factors, there should be 5. Let's force this to 5 and see what happens. And here we go. Hey, look at that. Check this out. That is pretty clean. Yeah. Well, let's go look at the correlation matrix.
Is the 447 okay?
What was that? In this case, yeah, 447. We have extra variables. We could drop it. I'd leave it for now. But we look at the correlation matrix, and there's nothing above 0.7. Oh.
So what is the structure matrix versus the pattern matrix?
Structure matrix is useless, whereas the pattern matrix is useful.
Good.
That is the extent of my knowledge on the structure matrix. But if you were keen on learning more about the structure matrix, here's what you could do. In the help topics, actually, I find they're less useful than just Googling. I was doing this over lunch, actually. I was looking up something. Somebody asked a question I didn't know the answer to, so I Googled it, which is what one does. But if you do SPSS, in quotes, structure matrix. And there it is, IBM's structure matrix and pattern matrix. And it'll tell you about each one. Oh, that's problems with it. And what is the difference between pattern and structure matrix? There we go. And they'll tell you about it. So I don't know. I've never had to know, but if I knew, would I be a better statistician? Probably. But I'm okay with who I am.
What's the difference between a pattern matrix and a rotated factor matrix?
Those are the same, just with different extraction or rotation methods.
It's the same for rotated component matrix.
Correct. Yeah.
They're just all the same.
They're all the pattern component and rotated component. Those are all the same. Yeah. Okay. So Rafael, we have a functioning pattern matrix. So that's exciting. We did have to delete quite a bit, unfortunately. Let me copy this over. Do you? Let me copy this over and just email it to you. I guess
Thank you.
You're welcome. I don't know if you end up using it because I deleted so much. I'm going to pause my sharing my screen for just a sec. But this will be something you can at least refer to as a possibility. There we go. And what you need to do with the things we removed, specifically, okay, let me share screen again. We removed the multi-dimensional one, the data sharing concerns. You might...
In that one, could I perhaps just choose the ones that are loading together and then remove the others so that maybe I just get one of the secondary dimensions, let's say?
Yeah, I can even, if you want, check this out. Let's see. If we go back to that one, this one, we can find the ones conceptually that load together. Problem is there's so many different dimensions. So you could do it that way, and then you see what you have. Or you could say, this is truly a formative index, and just calculate an average or something like that, and use a single score.
Okay.
Cool. Well, that was exciting. I was worried for a little bit there. I was like, every time I do this, I'm like, yeah, all right, questions here. Dr. G, I have the survey draft ready. Is there any value in exporting from SurveyMonkey to SPSS without any respondents yet? No, if you don't have any respondents, don't export your data because there is no data. On how, let's see, James, would you please repeat how to save factors? Yeah. So reminder how to save factors. If you go to your factor analysis, it's in the scores button here. If you click on scores, and don't do this until your final, like you've cleaned out everything and you're ready to move forward. Don't do this till your final EFA. But you just want to check the box for save as variables. And then hit continue, hit OK. Rafael, do you want this data set like in SPSS format, or do you not have SPSS?
SPSS format is fine.
Okay, cool. I'll send this to you with factor scores extracted and named. So when we go to name them down here, we look at factor 1, which was, go back here. Here we go. Factor 1 is effort expectancy. Effort expectancy, factor score. Factor 2 is performance expectancy, perf expectancy, factor score. And then viz risk, and then int, and cost. There we go. Cool. I'll save this and send this to you. Let's see, okay. Cool.
James, what's the factor score again?
The factor score is sort of a weighted average that has been standardized, where the mean is 0 and the standard deviation is 1.
What would I use that?
You could use that. Oh yeah, we haven't really talked about that. I'll show you what you can use that for. Let me email this real quick before I forget. I'm going to pause my sharing. I'm going to email this data set to Rafael. Here it is. There it is. Rafael, you're Escamilla, right? Maybe. hopefully.
Yes.
Okay, cool. Data set, see attached. Okay.
Thank you.
You're welcome. There we go. Sent. All right. Resume share. Okay. What do we use those factor scores for?
So it's a weighted average from.
Based on the weightings of the pattern matrix. Okay. And so what you could do is we could now actually just run a regression. You have a theory, right? You sent me a model. Let's do this. Let's run a little regression real quick. Linear. What's your dependent variable among these?
Intention.
Intention, all right. And I'll throw all these others. I know your model's probably more complex than this, but I'll throw these all in as independent variables. And then just hit OK. And here we go. We have a massive R square of 0.594. The model is a good model. That's the ANOVA table. And we go down the coefficients table. Cost is a terrible predictor of intention, but risk and performance expectancy and effort expectancy are good predictors. Notice risk has a negative effect, inverse correlation, inverse effect, whereas the others are positive. Cool. Those are your results right there. So you can do that with factor scores. You can also run them into ANOVAs or t-tests or whatever. Yeah. Or throw them into a path model. If we were to open up AMOS right now and generate a complex mediated model, we could use these factor scores. Okay, I'm exhausted.
All right, thank you very much.
You're welcome. Thanks for the data. All right, so I think we covered everything. What I'd like to do for the last 15 minutes is just, if you need help with anything individually, feel free to stay. I'll come and sit by you and I'll walk you through some stuff or answer your questions. Otherwise, you're free to go. Tomorrow, we'll cover all of CFA. It's a massive topic. Last semester, somehow we finished before lunch. And so afterwards, we just did causal modeling from Saturday. And then Saturday, we just did smart PLS and other stuff. We'll see what happens tomorrow. You guys might have more questions than last year, or less, who knows. But tomorrow's CFA. Okay, I'm going to stop recording. Yay! Oh man, that was exhausting.
James, I left you a seat right here.
All right. It's the end meeting.
Got all warmed up for it.